Okay, we're going to continue our analysis of functions with the exact same graph that we saw on the prior video, except now this graph is the graph of f prime, the derivative of some function f. So they're asking us to find the critical points of f, and remember that critical points, and I'll call them CPs here, this is where f prime is either equal to 0 or is undefined. So looking at this graph of f prime, you see that this graph is defined everywhere on its domain. So there are no places where there'd be a critical point from f prime being undefined. So we just need to look for where f prime equals 0. And we see that f prime equals 0 at x equals -2, 0, and 6. So those are going to be the critical points of the graph of f. Then they're asking what are the relative extrema of f and indicate what kind and why. Well, actually, we're not going to be able to find out the y values of the relative extrema because we don't have the graph of f, but we can find where they are. So let's do this. Let's just change this to say the where. So that means I'm going to give x values. So I have to look at each of my 3 candidates for relative extrema, which are the places where the derivative of f is equal to 0. And I'm first going to look at -2. Notice that the graph of f prime is negative and stays negative. That means the function f must be decreasing and still decreasing. Therefore, there is no relative extrema. Now let's look at x equals 0. F prime goes from negative to positive. So the graph of f goes from decreasing to increasing. So if f first decreases and then increases, we are going to have a local min of the function f at x equals 0. And again, this is the where, not the what. It's not the y value, it's the x value. The last critical point is x equals 6. At x equals 6, the graph of f prime goes from positive to positive, which means the function f stays increasing throughout, and therefore there is not a local extrema there. So in this case, there's only one local extrema on the entire graph, and it is a local min, and it occurs at 0. The absolute extrema, well, they can only occur either at a local extrema or at an endpoint. So our possibilities are at x equals -2.5, x equals 0, which could be a min, and x equals 8. So let's check each of these. And we have to think through this like we thought through the total distance traveled and net displacement problems on a prior problem. Notice that if I were to draw the antiderivative of the graph of f prime here, because f prime is negative on this interval from -2.5 to 0, the graph of the antiderivative function will somehow be decreasing. But then, since the graph of f prime is positive all the way throughout, the graph of f will be increasing on this entire interval. So I actually did not spend any time at all thinking through what this antiderivative graph would look like, except for to think through it would decrease and then increase. So the absolute minimum of the entire graph will occur at x equals 0. The absolute min, the where of it, is at x equals 0. The absolute max must then be at either -2.5 or at 8. But if you look at the area under the curve, the distance that this graph must have traveled downward is much smaller than this entire distance that the graph must travel upward. And so the absolute max is going to occur where x equals 8. Again, I don't know the y values here, and the absolute extrema are technically y values. I just can't answer that with this information that I have. Last question, where does the graph of f have inflection points? Well, f has POIs, points of inflection, where f prime has turning points. So let's go take a look here at the graph of f prime. We have a turning point. Changing my color, we have a turning point here. We have a turning point here. We have a turning point here, and we have a turning point here. Now keep in mind that when the derivative increases, like this entire interval here, that means f is concave up. Where the derivative decreases, that means f is concave down. which is why the turning points on f prime are the inflection points on the function. So I have 4 points of inflections on f, and they're going to be located where x equals, let's see, -2, at -1, at 3, and at 6. Last graph, last page, same exact graph, but now this is the graph of f double prime. And the only question we're asking you here is, where are there inflection points on f? So the only thing we can do with this graph, going back to f, is say, okay, well, if f double prime is below the x-axis or negative, that means the function is concave down. And where the graph of f double prime is positive, above the x-axis, that means the graph of f is concave up. So I'm just going to have one single inflection point on the graph of f, and that is at x equals 0, where the graph of f double prime changes from negative to positive.